Hi guys, welcome back to Aisha.Academy, and today we're going through exponentials and logarithms. Okay, so the general function when it comes to exponentials, this is before we jump into the E part, because I'm sure if you hear exponentials, you think E, hold up. So the general form is y is equal to a to the power of x, and this applies to where a is greater than 0. So a must be greater than 0 for this rule to apply. So here we've got a graph. So this is kind of like what your exponential curve would look like, slow grower and then gradually rapidly growing. So if your graph is is equal to a to the power of x, and your a value is greater than 1, not equal to 1, notice that it's not a greater than or equal to sign, it's just greater than 1. And then two things you need to notice is that when the x value is less than 0, then the higher the value of your a, the lower the graph, meaning like the less steep it would become. And then if your x value is greater than 0, then the higher the value of a, the higher the graph. Yeah, the more steeper, the rapidly growing. And we call this exponential growth. Okay. But let's say you still have the same equation, y is equal to a to the power of x. However, your value for a is not greater than 1, but your value of a is between 0 and 1. Then notice how the green line is not growing, it's reducing, it's going down. Okay, so with this one, if your x value is less than 0, then for values of a between 0 and 1, the higher the value of a, the higher the graph. So it's kind of like they swapped. Whereas if your x is greater than 0, the higher the value of a, the lower the graph. And we call this exponential decay. Now, two other important points to notice. With all exponential function graphs, or all exponential graphs, they all pass through a very common point. And this point is 0, 1. So that coordinate. And the reason being is because if you have a to the power of 0, anything to the power of 0 is 1. So that's why that is the case. The second thing I would like to notice is the lines actually don't touch the x-axis, and therefore your x-axis, aka the equation y is equal to 0, is always your asymptote. And lastly, a equals 1 is not considered because y is equal to 1 to the power of x is equal to 1 for all values of x. Example. So got a sketch graph here, and let's say the question says draw the graphs of y is equal to 4 to the power of x and y is equal to 0.5 to the power of x. So this would be our y is equal to 4 to the power of x because our a value is greater than 1, so it's going to be an exponential growth. Whereas our y is equal to 0.5 to the power of x is between 0 to 1, so it's going to be representing exponential decay. Both of these graphs, remember, they're going to both intersect the y-axis at 0, 1 coordinate, which I already explained why. So that's going to be the point where the two graphs cross. So that's going to be one mark for showing that. And your second mark for showing the equation of the asymptote, which would be the x-axis. But if it asks for an equation, don't put x-axis, always put y is equal to 0, because that's an equation. So what is E? We see E a lot, and I want to explain what it actually is. So E is basically an irrational number that is equivalent to 2.718. It's kind of like pi in a sense. E is like its own number. So y is equal to e to the power of x. It would be an exponential growth graph, okay? So if we were to differentiate e to the power of x, you need to know what it would differentiate to. And so the dy by dx of this equation, funnily enough, is just e to the power of x. So differentiating e to the power of x is literally the same as it would be. But if you have y is equal to e to the negative power of x, that is also going to show exponential decay. So not just values of a being between 0 and 1, but also if you have a negative power. The same thing applies if we have y is equal to a e to the power of kx. This would show exponential growth when k is a constant that is greater than 0. But let's say if this graph had the equation y is equal to a being a constant, a times e to the power of minus kx, because it's got the negative power, that is also going to represent exponential decay when k is greater than 0. This is very important to note. So if we were differentiating the y is equal to e to the power of kx, so the difference here is like, for instance, if you had e to the power of 2x, so value in front of x this time, the dy by dx would not just be e to the kx, unfortunately. The value in front of k is going to come in front, and so it's going to become ke to the power of kx. But if you were to differentiate y is equal to e to the power of negative kx, this would differentiate into minus k e to the power of minus kx. So it's basically the same principle as the previous one, just with negative values involved. So now we're going to head into some practice questions because I feel like it's just going to clear everything that I've explained up. So example 1. So in this example, it basically wants us to sketch this graph of y is equal to a to the power of x, where a is greater than 1. So here is the graph, and basically notice how it's intersecting the y-axis at 0, 1. So that's answering that point of any points that intersect the graph. And then in terms of any equations of the asymptote, in this case, the equation of the asymptote would be y is equal to 0. So that'll be a second mark there. And then the last mark, whether it's exponential growth or decay, is the growth, okay, because it's going up. So example 2. So here it's given us different equations and it wants us to state whether they're exponential growth or decay. So the first one, because it's to a negative power, is going to be exponential decay. The second one, because it's to a positive power, exponential growth. And the last one, negative power, exponential decay. I hope it's starting to make more sense now. Example 3. So it wants us to differentiate this y is equal to e to the power of 2x. So remember, it's kind of like differentiating the y is equal to the power of kx that I went through. So differentiating this would change it into 2e to the power of 2x. And then the second part wants us to find the gradient where x is equal to 0. So we know dy by dx is equivalent to gradient. We know that the dy by dx is 2e to the power of 2x. So we're going to substitute x into this, which would be 2e to the power of 0. So 2e to the power of 0. Anything to the power of 0 is 1. 1 times 2 is 2. And yeah, that's basically it, guys. So I hope that makes more sense in terms of the exponentials. My biggest advice is really and truly for A-level, you need to be doing past papers like as if they're your best friends, like as if they're your whole life. So keep doing practice questions on exponentials. And I hope this makes sense. Thanks for watching, guys, and stay tuned for more content.